quick. Output, path where the model checkpoints and logs will be saved. Um, per device, number of samples processed per GPU during the training. So I have one, so one GPU, so it's gonna process two. And then for eval, same thing. Gradient accumulation. This accumulates gradients across 4 steps. Let's be setting it to 4 here before performing a weight update. Effective batch size equal to 2 batch size times 4, then which is the gradient that's set, equals 8. So this batch size times the 4 gives you the 8. Okay, number of the training epoch, I'm gonna just set it to 3, which is pretty low. And the learning rate, as I mentioned, 0.002. FP16 that enables fixed precision training using float 16, and that's if it's supported by your GPU. For me, it should be fine. Reduces memory usage and speeds up the training. That's what you'll get from it. Evaluate epoch strategy. I'm just going to do evaluate on the validation set at the end of each epoch. Other options are steps and no, but I'll just stick with epoch for now. Login, I'm going to print log, loss, learn rate, etc. every 5 training step. And save strategy, I'm going to use that for which saves checkpoints. The model optimizer states at the end of each epoch. Report, I'm not going to report to tensor, weight and bias, or comment. And then provide my log directory, and I'm not going to submit to I'm not going to push the Hugging Face. I'll show how to do that later. All right, so that's the training argument. Now let's initialize the training, or the trainer. Let's initialize the trainer. Okay, I'm going to do this. And so what this line does, it creates an instance of the Hugging Face trainer class, this guy here, which is just a high-level training loop wrapper for fine-tuning or evaluating models. What it does, it handles batching, gradient accumulation, checkpointing, evaluation, etc. So you don't have to worry about you don't have to recreate all of that. We pass it the model from here. We pass the arguments that we defined here. We provide the data sets for training. It will use for training, and data sets for validation. The tokenizer, and that little fella there called the data collector. And what this data collector batches individual examples together, then it pads them to the same length and optionally creates labels. This MLM equal false tells it not to use masked language model. That's what the MLM stands for, masked language modeling, which is correct for casual LLMs like GPT and Llama, etc. It creates labels by copying the input unless already set in the data set. So important, just to note here, for casual LLM, The input and label are usually identical, except that labels are shifted next token prediction. Okay. All right. So let's train the model. So to train the model, what we're gonna do is just gonna train it. Trainer dot train the model. Let's explain that a little bit more, okay? This actually starts starts the training process using the Hugging Face trainer class. What it does, it kicks off the entire fine-tuning loop on the training data set it was provided with, and using the configurations. Sorry. Okay. So when this kicks off, this method performs the full life cycle, training life cycle, and this includes epoch and step loop, which it iterates over the training data set provided for the number of epoch, and we provided at 3. Divides the data set into batches using per device size and gradient accumulation step. Gradient accumulation, if you're using small batches, which is common with LLMs, gradient accumulation steps accumulates gradients over multiple forward passes before updating the weights. For example, given a batch size of equal 2, gradient accumulation steps equal 4, effective batch is size is 8, would be 8. Won't get into back propagation on this. That's the whole neural network stuff. So let me okay. So let's kick that off. Now let me make sure there are no errors in the code here. Don't think there are any. Okay, let's just kick it off. If any, we'll just fix it. Okay, while that's running, what I did was I knew this was going to take a very long time to run. I'm going to let it run, but let's just look at what the results will be. And the results will be what you see here. These are the epoch, the loss. What you'll notice is that the loss starts out very high, and over time, it drastically reduces. Let me pull up a graph that I have here. Okay, and I'll provide the code on this. So let's just look at it real quick here. So it started out the loss was pretty low, but it rapidly falls until it starts to stabilize a little bit more here. And the 3 epochs, which the evaluation losses happen at these points. Okay, so just a graphical representation of that same data here. Start loss, start at 4.2 here, and start fall rapidly. Let's interpret this result here. The initial loss 4.16, normal for starting, can be even higher, and then it takes early drop, rapid improvement to 2.5 within 0.5 epoch right here. Okay, and plateau at 1.9 to 2.1 after 0.8 epoch right there. And later stages, the loss started to stabilize at once it hits 1.86. Starts to stabilize right at 1.86, which is right there. Sorry, right here. As you notice, it started to stabilize around here. The learning rate from this to 0, you notice here by 2.3 epoch, and the gradient norm decreasing, and the training starts stabilizing. And there you go, the training is happening. This is going to take a while, and I'll show you the numbers on that. Okay, it's evaluation matrix. So eval loss it improves steadily per epoch, and the runtime and throughput were stable. Overfitting, none was detected. The training, however, took quite a while, and that's because the resources that I have is pretty low also. And I only did a batch of 2. It's going to take up to 20 minutes, so this is why I just let it run it, but it's not going to finish before. And then which is 1.049 training samples per second. It's pretty not good performance. That's okay for this. And anyway, this is the rest of the metrics on it, the summary on that. So overall, it was stable with improving loss and very clear convergence pattern. There were no overfitting, and evaluation loss improving with training, and the rest obviously is evident there. You can try to, if you have good resource, 5 to 10 epochs, if you know, for further, and investigate if you get further improvements, and at what epoch the improvements occur. Okay. All right. So while